Okay. So here we are. So we heard this word topology quite a few times this morning, and thanks for the speaker before me who already introduced quantum Hall in a way, so that I'm not going to bore you too much, but definitely I'm going to bring all of you together in the same platform as my understanding. So let's say we have heard since morning about all this kind of fancy states and how they behave. But as an experimental physicist, you know, what my concern is, let's say I know of a state which can have fancy quasi-particle in it, which can actually behave differently than the electrons that I know, but how I'm going to know that they are different? So often that can be electrical measurements, because you know we can always measure currents and voltages, and that can give us pretty much idea, you know, what it is. But that's really a good statement if the particles that is carrying the current or any other quantity in the system are charged. Let's say what happens if these fancy particles that we are talking about in many of the fancy topologically protected states are actually charge neutral. Then measuring just charge current is not a good tool for us, because you know we are experimentalists, as I said. I need to measure, I need to see if I see something. And there, apart from the charge transport, we have seen that maybe measuring heat flow or energy flow in the system, which you know doesn't need to be necessarily, you know, depending on the charge of the material, charge of the carrying particles, can be a good tool. And that exactly is the reason that we pursued it, and as I will go through my slides, you will see why it can be a good tool. So I will be definitely using fractional quantum Hall as my playground. Why fractional quantum Hall is just because that, as I said, that there can be different kinds of entities, not only electrons, but decorated quasi-particles that can behave differently. Or let's say the experiment will try to actually see if we can find things which are behaving differently into this kind of system. Okay, so the experiment that I'm going to talk about is just measuring thermal conductance. So before I go quantum or fractional particles, let's just put ourselves together, like just quantifying like what is thermal conductance. So we are aware of, you know, electrical conductance. So I'm subjecting a conductor to a voltage gradient and their current flows, and similarly if I subject it to a temperature gradient, then there will be a thermal conductivity because of the heat flow. And this is exactly what I'm going to measure. It will be a two-probe measurement of heat flow in such and such systems. So topological state of matter, like I already said, that this is a very recent review, and this field is full of this kind of reviews which just said that these are kind of, as I mentioned, fancy state of matter that can really give us something new to learn. And now, basically, why I'm doing fractional quantum Hall, because of the fact that this is really a first known topological state of matter. And it's very simple because electrons are confined in 2D world, and they often dress up as new entities. And the emergent particles are often known as anyons because they may follow any kinds of statistics, not boson and fermionic statistics particularly. And these quasi-particles are maybe neither boson nor fermions, but that has not been proved yet experimentally so robust way. And a very good quality of this fractional quantum Hall system or this quantum Hall system is that there is a bulk edge correspondence. So if there is something, let's say, is property of the bulk, that gets reflected through the edges. And the edges in fractional quantum Hall are basically conducting charge modes, which we can measure, thankfully, since centuries. So by just measuring the edge current, often we can also know about the insulating bulk. So in fractional quantum Hall or even quantum Hall, the edges are generally conducting the current and bulk is insulating. So what I'm going to do is going to measure charge current or fluctuation in charge current, thermal currents, and maybe interference of these kind of fancy particles that can arise due to interaction of electrons, and that will give us a rather detailed picture of this, complicated state of matter. The exchange statistics and why should be really interested in this kind of particles? Let's start with the particles that we know. So we know of these bosons in 3D or fermions in 3D. So bosons, we know that we exchange two particles, nothing changes there. In fermions, if a particle goes around another particle or it exchanges with another one, we know that it picks up a minus sign. But in general, in both the cases, if a particle goes around another particle, nothing really changes. But when we come to 2D, what makes this particle really special is now that they are restricted to really, moving only 2D plane, but not having another z direction to move around, they behave differently. And this way, what happens that a particle, like I'm just putting to the picture, if a particle goes around another particle, it picks up arbitrary phase, and this brings out this name anyons, like I said, any phase. But eventually what happens that if a particle goes around any number of particles, eventually it will be just adding up the phases that they have, so it doesn't matter in which order they are just taking turns. But this is a simple scenario. So if we have this kind of particles that, in which order they are taking turns of how many number of particles in this 2D plane, it doesn't matter. So they are these abelian particles that we know of. They are simple. And there is rather complicated kind of particle that we expect to see in this kind of system, known as these non-abelian particles. Because of their ground state degeneracies, when they go around each other, it basically end up in two different and multiple different states depending on what was the order of these exchanges. And particularly these kind of particles are interesting. Maybe a fancy name that you guys are all known of, all know of, this is Majorana or parafermions. So these Majorana or parafermions fall in this kind of category. And all I'm going to convince you throughout my talk and by the end of my talk is that this measurement of heat flow can be a good tool to really differentiate if there is presence of any non-abelian entity in the system. So again, my main platform will be fractional quantum Hall, and the reason for quantum Hall will be just accessing this 1D ballistic edge modes which carry all these fractional charges because of this interacting 2D electron gas, and study of anionic quasi-particles basically is already done for now it's almost 35 years. So we know that they are fractionally charged, there are neutral quasi-particles, and as I said, there can be abelian and non-abelian particles. So the bulk is insulating, there is bulk edge correspondence. So just to study the bulk, you can just study edge and you will have a good picture of the bulk which is insulating and often can host this kind of topological quasi-particles. So we study transport along the edge. So again, I'm not going to go through too many details, but 2D electron gas, when subjected to high magnetic field, basically have this kind of edge modes running around, which carries the current, as I said. And then there are this picture of the Landau level, like basically by changing the magnetic field, you can take this, through the various Landau levels. And these edge modes are really very special because not they are only ballistic, they have quantized conductance. And this was the first time that, almost 40 years back, it was discovered in silicon, and you can see there are plateaus which are, normal Hall effect doesn't have plateaus, but in quantum Hall we saw plateaus which were special, and then we tried understanding them, and that's why eventually came out to be this topologically protected state in fractional quantum Hall, etc. But what I want you to remember that there are these Rxx, namely the longitudinal resistances is 0, and the bulk of the quasi-particle bulk has localized quasi-particles. That is another important thing. Anyway, with time, what happens that as you go to lower and lower temperature, go to better and better samples, you see it's not only so the initial integer quantum Hall effect could have been just explained through Landau levels of electrons. But as you go to lower temperature, higher magnetic field, you see that there is resistance which is quantized to 1/3 electron charge, and that kind of tells you that, oh, I can now have quasi-particles which have charge which is less than electron. So this kind of experimental evidence led to the explanation, sorry, excuse me. Okay, so this was the first time that people have seen, plateaus with fractional charge, and there was soon an interpretation that how can we picture this kind of fractionalized plateaus in terms of electrons and flux quantas. And so far so good, let's say. And as the time goes by and you have better samples, better situations, and you can see that there is zoo of such fractional states which can tell you, okay, there are strong interaction and there are different kinds of quasi-particle that is available there. And the main thing here I want you to really focus on that there is some dip in the Rxx here at nu equals to half where there was no plateau. So the picture that basically satisfies known as composite fermion, where one electron is attached to two flux quantas, and then you can have Landau levels of these composite fermions, which effectively explains most of all these fractions. And then finally there was this puzzle which came out that you will see that all of the fractions have basically denominator which are odd, but there was this denominator 5, like the even denominator state 5 have, which came kind of 30 years back. The people saw that there is a state which is definitely having a plateau there. You can think about there is a gap state. But because it's even denominator state, people didn't know how to explain this. But eventually, of course, it's unexpected. And they thought maybe, just a kink, because often experiments are showing some data and maybe it's not real and it will go with time. But no, as you improve, you see things are improving. And yes, exactly, there was a plateau in better samples and stuff like that. And then you understand that, okay, so that means this is a true picture that I'm going to have a plateau in 5-half, and then think of an explanation that how can I have an even denominator, state, while Laughlin has explained all the odd denominators in terms of this quasi-composite fermions, if you can say. This is a picture by Jane. So the picture, as I said, for composite fermion is as if like two flux quantas are attached per electron, so that you can just effectively put this magnetic field to 0. And this is like symmetric, so Shubnikov-Dihas basically gives you the feeling that maybe this effective field here is 0 and that's how particles are behaving. And then Moore-Reid came out with this theory of like how two composite fermions can actually have a state which is similar to a p-wave superconductor, and that can explain this 5-half gap. So eventually what they want to say is like basically it can be a metal or a superconductor or any exotic phase. And the why superconductor? Because Rxx was 0, so longitudinal resistance is 0. You have a gap, you can think of a superconductor. And this can be a p-wave superconductor. Why? Because, because of the structure that we think. So Moore-Reid came with this theory that maybe it's a BCS polarized state of composite fermion. And this p-wave Cooper pair kind of generated the idea of this non-abelian state like Majorana fermions. And as you maybe know that Majorana is a zero energy state and stuff like that, and it's a neutral particle. How can we really realize in a system? So basically, this is just a pictorial representation that how Moore-Reid Pfaffian order is explained in case of a quantum Hall 5-half state. So basically, the edges are running where there's charge, and there is this Majorana excitation going on, Majorana mode along with this charge, fractional charge, and similarly, also in the bulk, there is inside the vortices there are Majorana anions there, and which, if present, should be non-abelian entity. Now, for the fractional quantum Hall state, as I already said, that they are predicted to host, fractionally charged quasi-particles. Fractional charges have been measured through short noises and etc., and it has been proved. But unusual fractional statistics have never been proved, and neither I'm saying that I'm going to prove fractional statistics here. So most of the experimental probes, as I said, are sensitive to charge. And non-abelian particles are often, as I said, charge neutral, and thermal transport may distinguish between this non-abelian and the abelian order. So first of all, let me just jot down what do we know before jumping into this experiment about the 1D ballistic channel and quantum limit of heat flow. So there was long time back, Sir John Penry suggested that this heat flow in 1D ballistic channel is universal for bosons and fermions. So namely, it doesn't matter if it's a ballistic channel, if the heat is taken by bosons or fermions, it should be quantized to the limit. Maybe I must mention this is the upper limit of the heat flow. So it doesn't really depend on the particle statistics. And then Ken and Fisher, after quite a while, took this work further, and they proved that even for abelian anions, namely for fractional charges, it should not be different either from bosons or fermions. So let's say all this Laughlin state that I said, that we have these odd denominator states that are normal anions that I said, the abelian states, they should also behave as if they are bosons or fermions. And then this was not proved. Let's say it was predicted 20 years back. And for non-abelian anions, if present in the system, I will be just talking about Majorana, like I said, because I would focus on 5-half state, which is supposed to host some Majorana particle. If present in the system, then the thermal conductance should be a half integer quantum of, like, the prefactor should be a half integer. Okay, now why half? Because of the fact that Majorana is thought of naively, I can tell you, a half of an electron. If it will be a parafermion, it will be fractional, but the number will not be half. So technically, if there is any non-abelian entity present, the quantization will not be unity, like the prefactor will not be unity or integer multiples, but will be fractionals. And that's the clue that we had to pursue this experiment. Okay? So experimental evidences, of course, as I said, like we were not the first one to measure even thermal conductance. So it was done before in phonons and photons, and it was proved Pendry right that bosons, and eventually this particular work in integer quantum Hall basically motivated us for further study. So all this works has been done and has been proved that yes, bosons and fermions don't behave different when it comes to heat flow in ballistic 1D regime. And I'm repeating myself about this ballistic 1D regime because I'm not talking about 2D limit, a 2D transport of heat. I'm talking about 1D ballistic flow of heat. And then it doesn't really depend on bosons or fermions, it behaves similar. And this, as I said, was our motivation for our work. And now I would just explain to you the working principle of the device, okay? So as we are going to measure heat flow, so definitely heat has to flow. So there will be a hot reservoir, which will be, of course, to a higher temperature. There will be a cold reservoir, which will cool down the other side of the conductor. And there will be this conductor, which will be conducting heat from hot to cold. And as I am, a solid-state physicist, I am in, solid-state system, I will definitely have some phonon into the system that will also dissipate. So basically there are electron-phonon interaction which will take some heat out of the reservoir for sure, right? I'm not completely isolated. And this electron-phonon interaction kind of goes as T to the power 5. But let's say now another thing that quantum Hall that I'm talking to you, it's we see in a very low temperature, in millikelvin temperature inside the fridge. So how do we heat this metal that if I want to heat something? Cooling down is simple because I can just, put it, short it to my fridge temperature and it will be cold. So we kind of dissipate power. And this power dissipation depends in our hand because we cannot, it's just Joule heating, you have a resistor, you pass current and it heats up. That's the picture. So if I know how much power I dissipated, and I know that this total power has to be dissipated either by the electron-phonon interaction, or this has to be, the heat should be transferred from between the hot to the cold reservoir through this electronic or quasi-particle channel that we will be having. Now for this 1D channel, we are relying on quantum Hall because quantum Hall gives us ballistic edge modes which are 1D in nature. So that's the reason that we use platform which is fractional quantum Hall. It gives us, zoo of particles to study and also ballistic 1D limit. Okay, and in the experiment we only measure temperature, namely nothing else but only temperature. And the electron temperature of the grounding contacts, namely the ground contacts means the cold reservoir in the picture that I showed. So I have to know the temperature Tm, which is the highest temperature. Let's say there's this hot reservoir temperature, there's this cold reservoir temperature, and this is what we measure in the experiment. And delta P is the dissipated power, as I said. Like we dissipate power because it's a dilution refrigerator. You cannot just go and light some fire there. So we have to use some batteries and stuff. So the control only we have is basically, if you remember the slide, the number that we want to measure is 1 picowatt. It's a very small number per Kelvin. So measuring a small number needs us to be very, very precise in measuring how much power that we are dissipating and how good we can actually measure these temperatures. So technically we can get rid of beta, how I will tell you soon. But eventually we want to really extract what is K. So by measuring Tm and T0 and knowing delta P, we are only left with one parameter. So we have to really do a good job by just measuring and knowing what we know about the system. For small temperature, you can all guess that we can just think about this term doesn't exist and only it's this, and that will be a good approximation. Anyhow, so this is a device geometry. Maybe many of you are theorists here, so I'm not going to daze you with the details of the device, but it's just to have a control of heat flow through this. So as I mentioned, there's a hot reservoir. The central metal island that you see this is the hot reservoir for me. So by flowing current inside, I'm heating this small metal up, and that in turn heats up all my edge modes that I depict by all the green arrows. And the temperature of these green arrows or green edge modes is what I measure through these detectors. That's all I do. Okay? And if you think it's too complicated, just know that it follows simple Kirchhoff's law. It's a simple circuit of quantum Hall resistors, all connected to a single point, which I can heat to different temperature as I wish. There's nothing fancy about it. Trust me on this. And I'm not, as I said, there must be many theoreticians. I don't want to daze you with the, details of this thing. So all you want to control the number of channels which gets in and out of this small reservoir. And by doing that, you can eventually extract what a single channel is taking in or out. And that's what we are looking for. And all we are going to do is going to go to different filling factors, namely different states of fractional quantum Hall effect, to change the particles that actually takes the heat in and out of the system, and to see if they behave differently or similar. And that's about it. As I said, it's a simple circuit. It has nothing fancy. And all I measure is as simple as this. So I give some DC current and I measure the fluctuation in the current. Okay? And this noise, which is thermal noise, because I have, of course, I'm not telling you that I am not supposed to introduce any additional noise in the system, because noise is the thermometer I'm using for my measurements. So I measure fluctuation in current or the noise, and this gives me the idea of the temperature in the system, and hence I'm not supposed to add any extra noise from outside or even create in the device additionally. Okay, so that is a background for the experimental preparation. And on top of it, whatever I measure is this extra noise, which definitely is proportional to the temperature of the system, because this is just simple Johnson-Nyquist. And now, as I said, in my device, the only thing I do is I just modulate the number of channels which is taking in and out the heat. So, I can have 2 channels taking the heat out, I can have 5 channels taking the heat out, and I just want to show you here 2, standard data set, just to show you that, how does these 2 graph changes, like how this graph changes as you change the number of channels. Okay, so you go to the same power, as you have less number of modes here, you go to higher temperature, while if you have too many channels to dissipate heat, of course, it goes to a lower temperature. Okay, but why we want to do multiple, channels? Because now if we subtract these 2 at this same temperature, that will get rid of the phonon term, because phonon doesn't depend on how many channels are present there. Because the phonon that I'm talking about, it's mostly the reservoir, that the small ohmic contact that I had in the center, the electron phonon interaction there particularly. Okay, so if I can take multiple of such data, which I took, and then I can take differences, etc., and that eventually get rid of this phonon term, and that get rid of this phonon term. And as I measure Tm and T0, so I measure these 2 quantities. This J total is the dissipated power that I have for the system. This is the only prefactor is what I want to measure. Sorry for dropping here a prefactor, which can be just delta n we can write. Okay, so that's what we are trying to get out of this data. Now, as I said, that Ken and Fisher said that for 1 channel of composite fermion, which is like this let's say E/3 charge, it should be similar to electrons. which should be like 1 unit of kappa naught, which is basically this perfect number, because it was, if you paid attention, there was all natural constants. And this is what we measure. So if you see the slope, basically this y-axis, I just named it something, but it's basically is a normalized to the number of mode that you have, and the slope will give you what is the prefactor of the unit of thermal conductance that you should have. So here for 1/3 state, like nu equals to 1/3, we see that the slope is very close to 1, which for experimentalists we are really happy, because this is this is a good agreement. So far so good. As Ken and Fisher said, that if it's a abelian anion, it should not behave differently than electron or bosons and stuff like that. And then we go to more complex states. Why we go to more complex states? Not just because it's freely available for fractional quantum Hall, because yes, if I go to fractional quantum Hall states, I will get zoo of states, as you said, and it's really good to do experiments in all of them, because somebody has to do one day and you can publish. But our motivation was no, it's often that. But the point is, at the end of the day, you should have a better motivation, and our motivation was this. That we knew, because as I said, quantum Hall is now a 40-year-old subject, a field. So we know that the states between half and nu equals to 1, so filling factor 1 to filling factor half, there are several states like 2/3, 3/5, 4/7, and more, which I'm not saying here. They have been basically experimentally proved to have some neutral modes alongside the charge modes. And these neutral modes are basically what motivated us, because these neutral modes that are present in this kind of states are supposed to be bosonic neutral modes. They should not be, yes?
Could you go to the previous slide?
Yeah, sure.
So when you measure the heat flow in the 1D channel, are you involving both edges or only one edge?
So basically, its heat is always going from hot to cold. So the both edges comes exactly when I'm going there. So if you go to this complex, news like 2/3, 3/5 and stuff like that, where there is counter propagating edges, then you need to actually think about both, because otherwise think about it. Right. It's chiral, so it doesn't matter when cold edge is coming to the reservoir, because I'm measuring the equilibrium.
In the experimental nu equal 1/3.
Yeah.
Is the other part of the edging, did you?
Yeah, so the other part of the, so it's basically chiral. So let's say 1/3, we have this picture for long, length of the sample. We imagine there is only one edge which is going down from left to right, let's say. And let's say my left is hot, yeah, and my right is cold. Okay. And what is going on the other side, it's cold to hot, so that is definitely not taking heat out.
But you're not doing anything to the other part of the edge.
No. I'm not. Actually, if you remember that my device is 2 probe, so I'm shorting in either side. Like my both edges are shorted, so they are connected to the same contact. I'm not doing anything because it's a 2 probe device.
2 probe device.
Yes, I will be considering them for sure in 2/3 and 3/5 and stuff like that. Yeah. So, of course, I already said about this kind of, they have upstream neutral mode. The upstream is the extra information here. Upstream means the downstream is what, goes from your higher mu to lower mu, higher chemical potential to lower chemical potential. But these states, they have proved experimentally to host, upstream edge modes. Namely, it's going in the opposite side, opposite direction from lower chemical potential to the higher chemical potential. And often has like an experimental proofs are there that they are in general neutral modes. And as I said, that these neutral modes are bosonic. And if we really want to distinguish about charged and neutral cases, and Majorana being a neutral particle, we really wanted to have situations where things like where it was not supposed to be a non-abelian state, and yet we have some neutral entities so that we can calibrate ourselves. Okay, so that's a good calibration for ourselves, that yes, there are neutral modes known. Let's see how they behave. Okay, and in this case, as you see, there are counter-propagating edge modes. Ken and Fisher kind of suggested what should be the number. Now the numbers are, as you can see, it's 0, -1, -2. So 0 because, it's like there is equal and opposite. But this number is going to be true only in thermodynamic limit. Namely, if it's a small sample, it's never going to mix so well. So what it suggests basically, that whatever heat this will bring, the other will return. And that's the reason the conductance is 0. But this is true for a long sample, namely thermodynamic limit, for that matter. And in this case, as you said, like in this case, both the edges will be important, because then in either edge you will have heat carrying modes, and that's what we want to look at. And do not be feel weird that why there is negative, because that means, oh, heat is going from the cold to hot. No, it's not. It's basically because of the fact that the quantum Hall has chiral edge modes, so the edge modes are continuing. So whatever is in the, let's say now we have a 2-probe device, so both the edges are like exactly opposite. So whatever is carrying heat from the bottom edge, let's say this is the bottom edge, let's say, and whatever is carrying heat, so here this edge is carrying heat, and these two are coming from the cold side. But on the opposite side of the mesa, these two will be carrying the heat, and this will be the cold one. So basically, whenever it's negative, all it says, it's the other edge which is conducting the heat, not this bottom edge. Namely, it's not carried by the mu greater than 0 side to, mu goes to 0 side, but the other side. That's all the negative is about. If I'm basically making you a bit puzzled, you can ask me a question later. In any case, in my device, because it's 2-probe, I'm only going to measure the the modulus.
So
yes.
Does that mean that when it's negative, the charge current is going from one part of the edge, while the heat current is flowing from the other part of the edge?
Yes, exactly.
Sort of a charge-heat separation.
Yes, in a way, yeah. Okay, so why 2/3 should be 0? Like as I just briefly mentioned, that you have an edge which takes the heat out, but then there is another edge which takes the heat back. So basically, if there is interaction between these two edges, which was I'm not going into all the details why it is there, but it is there, and that's the reason that you eventually mix up stuff and can end up with 0 thermal conductance. And as I mentioned, this 0 will only result from the full equilibration and large length of the sample, so that all emitted heat is returned. Only then it will be 0. If the equilibration is not full, then you will not see 0. Okay? And this is the result. So this is the result for 4/7, 3/5, and this is the result for 2/3. 2/3 we should see 0, but we don't see 0. So I only want to say that for 4/7 and 3/5 we are close to the quantization that we're supposed to see, which tells us that yes, neutral modes, at least in these states, behave exactly like the electrons or the bosons that they should behave like exactly Ken and Fisher said. But in case of 2/3, we end up being not 0. Not only not 0, just look at the number. It's almost 1/3. It looks like magic. It's 2/3 state and heat is quantized to 1/3. We are experimentalists, but we think, okay, that has a ring, okay? So you now question, maybe it was not right. Maybe all this Majorana, you don't need Majorana. Even having a normal neutral mode, you can have fractional heat conductance. And then we wanted to dig in more. So I could not change the length of that particular sample, but what I can do, I can always increase the heat, temperature, the temperature of the lower, the cold reservoir, basically. And if it is a quantized quantity in 1/3 of that kappa naught, it's a God-given number, it should not change, right? That's what topology tells us. Like, it should not change. The thermal, quantum Hall doesn't change its conductivity because you change 20 millikelvin temperature, right? So it should not change, but it changed. And when we started doing this measurement, of course, we were not as smart, but later on we figured out that why it is like this, because exactly there was not full equilibration. So the sample length was not enough to equilibrate for this 2/3 equal and opposite heat carrying. So that's what explains this picture. And if any of you is interested, I can go into details. And here I will just touch upon it. So we kind of got a very, very, hand-waving theory for it, that if we can just think of some interaction that, you exchange the heat between two edges. And in case of 2/3, it's a special case because you have equal and opposite. And because it's equal and opposite, you need longer length in order to really return all the heat. Because, as you increase the length of the edge, there is a possibility all the heat will return. But if it's not equilibrated completely for the given length of the sample that we have, all heat doesn't get back, and that's why you have some conductivity of heat, okay? And for 3/5 or 4/7, why it was ideal and followed Ken and Fisher is just because now you have more number of edges. So basically, what does that mean? That means that you have putting a weightage in a certain side, and that's the reason for 3/5 and 4/7. What happened? That these numbers are not same. They are not like 2/3. All are 1/1. It was in case of 3/5 it was 2 as opposed to 1. In case of 4/7 it was 3 opposed to 1. So that's why you can explain their equilibration faster. And this is the model that we think you have question.
Do you have higher temperature data for the?
So I took only for 3/5.
2/3.
Yeah, 2/3. I took only until.
You only go to 30.
30,
right?
yes, because
but the energy gap for 2/3 is quite high, right?
Yeah. The reason we don't go, if you remember again, we are measuring a number which is 1 picowatt. And the reason for not going to very high temperature is this, because then the phonon time will be relevant. And I'm going to subtract, I told you like my experiment is like, I'm subtracting 2 curves in order to get rid of phonon. So I will be subtracting 2 small numbers which are close by to get another small number. So the more you go to higher and higher temperature, the electron phonon interaction takes over. And I wanted to be in a regime where, it's that I do not really phase out my entire measurement. Nothing else. Like I did also in 40 millikelvin. I just didn't put the data because it was going down. But as I said, the data was really, it was trained. And you will just tell me, how you are just drawing this conclusion. So that's the reason we stop here.
So is it possible for your data to estimate the electron phonon interaction in this temperature range? So at what temperature the electron phonon interaction is?
So we have seen from all our data, it's like, after 40 millikelvin, that's what we have seen. Like I've shown also in the data, you can see it's really bending. But this bending is only after, because it also depends on T0. As I increase the T0, it starts even to start with, it bends a lot. Yeah, that's the reason, nothing else. Like you can always subtract and there will be always difference, but it's a very small number, so the accuracy will suffer. That's all, nothing else, yeah. So this is basically the model that we had, and we could plot, and we can see that, we just wanted to see if it will be forced for all these states, given a certain length of the sample, how the conductance will be converging to the ideal quantized value. And we see, yes, for 4/7 and 3/5, it goes faster than 2/3. And like I said, 2/3 is a special case because you have equal and opposite, heat carrying or cold edge modes. That's all. Okay. So what this graph tells us, it tells us not only that, the Kane and Fisher was right, but also if we have bosonic neutral modes, they will be carrying equal amount of heat as electrons. This was a good information for us because we really want to look forward to some other kinds of neutral mode in the system, if at all possible. Okay, so this is so far was the summary. And now, what do we know about 5-half state? I think I told you guys already that 5-half was the first known, different state. But I didn't tell you that already there were measurements of the charge. So, okay, so basically, Moore-Reid and similar kind of wave functions predict that the charge should be over 4, like the excitation should be, fractional excitation should be over 4. It was measured experimentally. Also, there are states or wave function that explains that it should have upstream neutral mode. And when I say this upstream neutral mode, that can be bosonic neutral modes as well. And it should be a spin polarized case because it's a moderately high magnetic field that we saw this kind of states. That's why it should be spin polarized. And all these things have been actually seen in experiments. But as you always know, for experimentalists, we do everything, but then there is another question. Nobody says there is Majorana. You see? So, okay. Kenneth, Moore-Reid said you should see these. You see them. Do you see Majorana? I don't know. So it's still, that's the question we are fighting, because it's not that we are just writing stuff and we are thinking, we should have. It's like we should have, we could have. Do you have? That's the question for us. Okay. So it's not me, who's doing this. It's like all of us in this field are like this. So yeah, there are piles of stuff, but yet non-abelian or non-abelian, we don't know. And here comes our measurement, because to tell you the truth, if this fails, then of course maybe it's really non-abelian. It's an abelian state. Sorry. So the 5-half were studied at some point of time quite rigorously because it was really exciting and was first time experimental condensed matter system that you can see this kind of possibility of Majorana modes, which can be, I don't know, doing so many things. So there are people who are really ambitious and they thought, okay, Majorana can exist. And they suggested this kind of wave function for the states. I'm just giving the edge modes according to their theory. And then there are people, they think, well, all these things can be true, but without Majorana as well. And that's a good thing. Like I said, this is what happens in experiment. You see a peak, but then what it is, you never know. So you see, so there are 9 different possibilities, and thank goodness that there is some quantity that differs, and this is this thermal conductivity. So the thermal conductivity measurement should be a good tool. I cannot tell you that yet I finished the puzzle, but yeah, it's somewhere there, we are closing. So anyhow, so the point is, eventually if you measure something like this integer, you are good, you don't have Majorana, you can go home, start afresh. And if you land here, okay, it's a good idea. Maybe we can do better, but yet not sure. So let's see what do we get in experiments. Of course, we are experimentalists, we cannot get lucky. It just doesn't happen. So you measure, you start measuring, and you see a number which is, by the way, first of all, this 2.5 is not a good number. Liang knows about it. He will tell, but pH Pfaffian is not a good number. But, but the point is, we were thinking of anti-Pfaffian, which should be 1.5. To start with, my heart was broken. So I'm like, okay, never mind, something. And then you go to lower and lower temperature, you see this number is rising. As if it's pushing itself to 3, I was like, better, once and for all, things will be done. You don't say any more Majorana, no Majorana, whatever you have, this is what you have. So, but we are also a bit, I don't know, greedy. So we still want to, I don't know, maybe. So these are the numbers that you measure. I couldn't go lower in electron. When I say T0, this is the electron temperature that I have. My fridge was 4 millikelvin, but pushing electron temperature to 10 millikelvin is already good enough. I mean, like maybe many of you can be doing better than me, but I was like, enough of problem, and this was not going below 10 millikelvin ever. But anyhow, whatever it is, it's nowhere good. It's just not good. It's something fraction, but I don't know, But I was still thinking, how can I push it towards any conclusion? And then my supervisor kind of likes to plots it like this, See, we are approaching somewhere, and it's not an integer, and if anything, it's very close to a half integer. So this is the only positive outcome that we have. But let me say this, that maybe we are not completely being greedy here. Our experience with 2/3 told us that equilibration in this kind of cases are not so simple, and they can be often a bit complicated. And given that if we really think that there can be a possibility of having a Majorana edge mode running around, that should not have the similar kind of Fermi velocity as the other edge modes and stuff like that. So that makes a case that maybe we should see some discrepancy, but I must admit I was really disheartened, as we are measuring for edges and nothing comes out. Yes,
Do you have any data for 7/2?
7/2, actually the RxX was not completely 0 for me, and it was very close to 4 that I measured. And the reason for RxX 0 is important for us because, as I said, we are measuring in a certain way, and we may lose signal, which can give us wrong result.
So what's the energy gap for 7/2?
I think this one was 220 millikelvin. I think 7/2 was even lower. Like the plateau was, very narrow, and the RxX were never 0. It was like 8/3 for me. It's like 8/3 has also the similar problem. So if for any of you it's a bit puzzling, what we are talking about, it's like, in the measurement that I'm doing here, I wanted all the heat to be carried by the edge modes because, I made a statement that I'm only giving you information about 1D ballistic edge modes, and they are necessity in my case because I can only talk about 1D ballistic mode because the energy is quantized there. But if I have some longitudinal resistance, which means that I have some backscattering that tells you that heat can be lost from the bulk to the ground by various means, it doesn't necessarily have to go through these edge modes. And for my measurement to be, technically right, I have to have a situation where I know all the current is taken by the edge modes, so that's the noise that I'm measuring. Okay? So here we are, maybe very positive to think that we maybe somewhere have nailed the point that yes, maybe this is a system in condensed matter that we can have Majorana modes which behave differently than other particles that we have seen so far. But yet I cannot tell you that I have proved, non-abelian statistics or something. Like I always say, you do something, but something is remaining. So we have to still braid them in order to see if they are really good enough for what they are thought to be, and that we are after them. So the number that I show here, I must admit that they are not the favorite of the theoreticians because for the people who worked a lot on these kind of states in order to understand them, because particle hole symmetric Pfaffian should not have some gap, and that's the argument for that. But somehow experiment goes there, and I have no hands on them. In 2 different kinds of devices, we saw this kind of similar results. So I stand by my result, but I would be happy if somebody can prove me wrong or right. So you are welcome. And as I said, that there are many theoretical possibilities. Our previous speaker also, I'm thankful to him, he also published a paper, just explaining that yes, weird things can happen and can be explained. And the picture can be that, so there are this Moonread basically gave a picture of Papian, and there can be an anti-Papian picture, just a whole picture of that. Let's say if Papian is a particle picture, you have a whole picture, and you can have this particle whole puddles next to each other, which can give you effective pH Papian, which may look like a pH Papian order. But actually it's a mixture of all these particle and Papian and anti-Papian state. But my favorite theory is Steve Simon. He says maybe it's an equilibration issue, and maybe it is. And now I'm not in Weizmann, by the way, this work was done in Weizmann. These are my collaborators. These are the theory collaborators who taught me a lot about how to deal with data and when to face the world and justify what you see. And this is my mentor, and he's very optimistic. He's way more optimistic than I am, and he is continuing. So there is. So I'm currently in Colombia, starting to think about twisted graphene and stuff like that. So things move on, right? It's like you have to move on. It's like my Rana, it's good, but maybe I have to twist and turn stuff because you never know. You never know. So they're actually continuing work on 2/3 because we really want to understand the equilibration process. Namely, you have counter-propagating edge modes, and I would say, definitely graphene is very, very interesting because, like people say, they are very accessible to everybody. But I love personally gallium arsenide because of its stability. Because if I am really happily sharing my result today with you, which is not a simple experiment, and it has been done to great details, and the numbers that I'm quoting are small, yet I'm confident because of the system, because it is a very stable system and tried and tested. And hence all I will say that I believe in what I got, and I will be happy if somebody proves me wrong or right, and that's it. Have any question, I will be happy to answer.
So questions, people?
Please.
Yeah, do we know that at the 5-Hz filling in your sample, the bulk is thermally insulating?
Yes, so basically in the 5F sample, like you want to know if the bulk was, yeah. So basically what we try to do, as I said, the RXX is one thing that we try to see if the longitudinal resistance.
That tells about the charge conductance.
Yes, and also we try to measure, this upstream neutral mode to short distances to see if I see something, and we saw, upstream neutral mode for short distances, not for long distances. Yeah, this kind of, I just didn't say because, for people, they will not care. Yes, we did this kind of checks, for sure, yeah. Yeah.
So I heard some proposals saying that disorder may stabilize one phase or the other. So have you tried samples with different qualities?
Yes, so basically we did, so my initial result was on the SPSS structure, which is the old canonical structure. So from our lab, where in this similar structure, we measured E over 4 and neutral mode, etc. But this was also got 2.4, 2.45, something like this. And then, but the problem with this structure was that it has heat conductance to the bulk that we guessed, because when we took differences, it was good, like all these graphs, but individual number gave us some additional numbers. You see what I mean? Like I should have 3 channels, let's say 3 times kappa naught is what I should measure, but I saw 6. And this number constant was added to all the number of channels that I can have. So, and all these measurements that we used to do for fraction, we first do it in filling factor 2 because, filling factor 2 and 3, because we want want to make sure that integer really falls in right place. So for SPSS structure, that is what we saw. We saw that there is some additional heat conductance alongside with the number of edges, which if you subtract, because I'm subtracting at the end of the day for n channels and n plus 2 channels, let's say. But for n channels, I do not measure n. I measure n plus something, which I also measure from n plus 2 plus that something. And then we go to this other structure, which is just dx center, but either side. And of course, its mobility is low. It's 20 million from 35 million. But we got similar kind of result, but not the excess heat conductivity. Yes, we tried, and I definitely measured more samples than this, but yeah. Any other question? You had some question, yeah.
So, did you check all the pair of quantum point contact for the current flow? Because you need to control all your quantum point contact to control the edge flow.
So here what we do, generally use the quantum point contact to close or open. So for fractions, we do not manipulate them. For 5 what I did 2 and 1 and the entire, but never in between, because we don't want to, like I said, if you have partial transmission of the QPCs, you will add noise, which I don't want. Yeah. Any other questions? Yeah, sure.
If I understand correctly, so all the measurements are measuring the two-terminal.
Yes.
So,
yes.
Is it possible to measure directly the thermal high in the future?
Yes, you can do. So basically, you can put QPCs and do it. But to start with, this was good enough to even push there. Trust me, it was. I hope you get the picture that it's very easy experiment, but it is not. So, yeah. Yes.
Yeah, in these two terminal measurements, when you have a temperature difference between the two terminals, you're measuring the heat current. Is there also a charge current?
Always. So basically, I do not measure the heat current. I just measure the temperature and model it into, if this much power dissipation flows how it should be. So namely, the equilibration temperature is what I'm measuring, which in term is like heat, but charge, of course, because it's quantum Hall, so I have the RH. That's the electrical circuit for me. So my electrical circuit is very simple. It's the R Hall of that particular nu connected to a single point, which is this reservoir which heats up.
Right.
That's all. Yeah. I'm not measuring heat flow in that sense. I know how much power I'm dissipating and how much the temperature is rising, because that comes out of the equilibration of in and out of the heat, right? Like the edges are going in and out, and I'm measuring the equilibration temperature of that reservoir, because I'm measuring far the fluctuation, which is 4 kVTR.
The dissipated power, how is that measured?
Oh, so that's basically, as I said, it's a simple Kirchhoff's law. I have all the RH combination, and I put some DC current, and I know how much. You can calculate. If you, yes, yeah, I can. Sure.
How you check the contact resistance so that you know the power?
So I don't have to check the contact resistance, but of course what we check is that if I send current, if I'm getting as much current as I'm supposed to get in all the terminals. Because this equal branching of the current is very much important, because this small reservoir is supposed to have zero resistance to all the edges that is going in and out of it. It should be an ideal ohmic contact, but not too big, because if it's too big, I will have a huge electron phonon turn. If it's too small, the edge will go in and out, not equilibrate. So there is a sweet spot, you have to have a right size, which still give you a good ohmic contact and a good thermal reservoir. Yes.
When you say you put 1 picovolt, how can you know it's 1 or it's 1?
Oh no, this is like, as I said, so what kind of check is what kind of check that you can do is if this is an ideal contact or not. If it's not an ideal contact and it reflects back some current, you push some current, there will be one terminal you will get more current. because it's quantum Hall and I have both the edges together. So yeah, there are tricks, like if you are interested, this is what first of all we have to do. And if I don't do this, I will get a wrong result, and that explains later on why I didn't get that. So yes, we always checked for it. So it's really nice because of the quantum Hall that I don't have to have additional contacts or wires going to the central reservoir, because the edges itself are current carrying wires, which goes in and out, and that's the trick actually. That gives us this amazing handle to know the delta P, the power that we dissipate, to such accuracy. Yeah. Any
more
other questions?
All right, let's thanks the speaker again.